Question 16. Steel ball bearing released and folds in a tall cylinder of clear oil. The ball bearing initially accelerates but soon reaches terminal velocity. Complete the free body force diagram of the ball bearing when it is moving at terminal velocity. So key idea here, terminal velocity, the forces are equal and opposite. When we draw free body force diagrams, the arrows have to be representative in terms of size. So when you are drawing the arrows, the length of the arrow does matter. So when we are looking at terminal velocity, the forces, the arrows should be equal and opposite in size. So all forces should be labeled correctly. So when a ball is falling, it has weight acting on the ball. So I've drawn it with an arrow with W for weight. You've got the object is moving. So it has some drag on the object, but it also has some upthrust on the object as well. So note that the size of both of these arrows are very similar to the size of this single arrow. So this is equal to this in length. So U plus D in length is equal to W. Okay, so when you have an object that is falling, the upthrust and the drag are acting in the opposite direction to the motion. The motion of the object is downwards with a terminal velocity. Key idea, the terminal velocities of these two are equal and opposite. So if we have a look at the following question, it says write down an expression which shows a relationship between these two forces. So if the object is moving at terminal velocity, therefore the weight is equal to the sum of the upthrust and the drag. The next question here, you've got a ball bearing, diameter 3.5 millimeters, falling at terminal velocity, just as the previous part of this question. And we've got the terminal velocity equation that we need to know how to derive as well, but it's been given to us. And we've got some other values. We've got the density of the steel ball which is falling through the oil, and the density of the oil given to us as well. So let's have a look. The diameter is given of the ball bearing. However, there's no diameter in this formula. It's radius, so we got to do something to that. It's given to us in millimeters, so we need to change that to meters because we're using standard units in all formula. And terminal velocity, it's there we go. That's the value for the terminal velocity. And again, it's meters per second as our standard units. That's centimeters per second, so we need to convert that as well. And the density is also in grams per centimeter cubed, so that we need to convert into standard units of kilograms per meter cubed. So let's have a look. Let's convert the diameter into radius and into meters as well. So 3.5 millimeters divide by 1,000, and that's 3.5 times 10 to the minus 3 meters. The radius is half the diameter, so that's 3.5 times 10 to the minus 3 over 2, and that will give us the diameter in meters. Now, the velocity is 3.4 centimeters per second. So we've got 3.4 meters centimeters per second here, and we need it in meters per second. Centimeters to meters divide by 100, so that would be 0.034 meters per second. So we've got the velocity in the right unit. Now the only thing that we need is the density in the right unit. So to convert grams per centimeter cubed into kilograms per meter cubed. So let's have a look at this. So we want to convert that to kilograms. So grams to kilograms, what we have to do is we have to divide by 1,000, which is the same as times by 10 to the minus 3. Okay. We also, let's have a look at the centimeters cubed, which is at the bottom of the unit for density. We've got to get to meters cubed. So centimeters cubed to meters cubed, what do we have to do? We have to multiply by 10 to the minus, well, it's centimeters. So it's 100 centimeters in 1 meter, and it's cubed. So that's 10 to the minus 6 to get from centimeters cubed to meters cubed. And we've got times 10 to the minus 3 at the top, times 10 to the minus 6 at the bottom, and it's divide. So it'd be 10 to the minus 3 minus 6, and that ends up as being times 10 to the 3 to get to kilograms per meter cubed. So multiply by 1,000 effectively to go from grams per centimeter cubed to kilograms per meter cubed. So here 8.05 grams per centimeter cubed is equal to 8,050 kilograms per meter cubed. So think about it. 8.5 grams in every centimeter cubed. 8,500 kilograms in 1 meter cubed. That makes sense. Okay, so look at the numbers. That'll be 8,050 kilograms in 1 meter cubed and 8.05 grams in every centimeter cubed. So look and think with the numbers of with whether they make sense, and then putting everything in r squared 2 times r, and I've rearranged the formula as well. So it's the viscosity is equal to 2r squared g. The difference in the density is divided by 9 times the terminal velocity. I put the numbers in, and we get a number of 1.43, and the unit for viscosity, we'll have to remember, it's not given to us in this question, is Pascal seconds. You could convert that into standard units, but it doesn't really ask for that. So how are the marks split? You need to convert diameter, velocity, and density, and you need to put in the numbers into the right part of the formula and rearrange correctly and get to your answer of 1.43 Pascal seconds. That's how we get to our 3 marks. Okay, right.